this is basically using the formulas which I wrote down some time back about the transformation of stresses. So let's get to it. Let's call this 1 and 2. 1 and 2. So first I'm going to write the formula for principal stress. So that is sigma A B equals sigma x plus sigma y divided by 2 plus or minus square root sigma x minus sigma y divided by 2 square plus tau xy square. So that's the principal stress. Let's compute that. Now, before we do that, we need to identify what sigma x, sigma y, and tau xy are. So this is where the convention is slightly different from what we use for Mohr's circle. It's the same for stress. The stress sigma, it's slightly different for tau. So for sigma, tension is positive, and so you see that it's, in this case, the stress is negative, so because it's compression, it's 80 MPa. Sigma y, you can see that's under tension, so it's 50 MPa for y. However, this is how the shear stress is different from the one used for Mohr's circle. For Mohr's circle, if you go back, you'll see that Mohr's circle, we assume that clockwise is positive. Right here. Clockwise is positive and counterclockwise is negative. Here, however, we'll take the normal convention, which is clockwise is negative and counterclockwise is positive. That's the difference between using the formula versus doing it through Mohr's circle. So tau xy, in this case, if you see face A, it's clockwise, and so we'll put a negative there. Okay. In fact, if you go back and see the derivation, which I think I posted now, the derivation was based on this diagram. Okay. In other words, if you now compare this diagram for the stress, you see that the stress on face A is counterclockwise, and that was taken to be positive. And here we have the stress as shear stress in the clockwise direction for face A, and so the stress is negative. So this is because of this. This is the convention. Okay, so just be mindful of that. It's slightly different from what we use for Mohr's circle. So now we can sub these values inside this formula, and essentially it's plug and chuck. So if you sub in the values, you get sigma A B equals minus 80 plus 50 divided by 2 plus or minus square root minus 80 minus 50 divided by 2 square plus minus 25 square. Okay, and solving for sigma AB, we'll get, for the first thing is minus 15. The second part is basically the radius, which is 69.6. And so the answers are sigma A is 54.6, taking the positive sign. And then sigma B, taking the negative sign in the above expression, we have minus 84.6, which, and of course the shear stress, when the principal stress is maximum, the shear stress is 0. So this is the answer for part 2. And if you compare this, so for example, remember 54.6, go back to the previous lecture. Our answer was 54.6 and 84.6. So that checks with what we got using the formula. The next is to find the principal stress direction, and that is again goes by this formula. Tangent to theta p equals 2 tau xy sigma x minus sigma y. So just plugging values. Minus 50 comes out to be 0.3864 or 3846, I think. So 2 theta p equals 21 degrees, which boils down to 10.5 degrees. Okay, which, by the way, is the same as what we got using trigonometry. Just quickly swing back. We had here 21 degrees, 10.5 degrees for theta p, and we use trig here. So what this answer tells me is that it's 10.5 degrees counterclockwise to phase A. Okay, so if you draw the plane stress elements in its normal configuration, then you need to rotate by 10.5 degrees in the counterclockwise direction. (10.5 degrees). This indicates, the positive indicates CCW. CCW. Okay, and then you can fill in the dots based on the previous problem. Now, let's solve part 3, which asks us to solve for the shear stress. The formulas for part 3 are as follows.
Professor, I'm sorry to interrupt, but is there any way you can go back to the where the equation is for sigma AB with just the variables? Not with the numbers, but the variables. Okay. Okay, thank you.
Okay, so the formulas are as follows. The max min stress are given by plus or minus square root of sigma x minus sigma y divided by 2 square plus tau x y square, which comes out to be minus 80 minus 50 divided by 2 plus minus 25 square, which is plus or minus 69.6 in MPa. Okay, and then the formula for stress corresponding to the max and min stress is given by sigma x plus sigma y divided by 2. So that's minus 80 plus 50 divided by 2, which is minus 15. Okay, we can quickly go back and check if this is the same answer we get using the other method, Mohr circle method. So 69.6 and minus 15. Go back to here. So we have 69.6 for the stress, and I did not quite show the principal stress is right here, minus 15, right? Okay, and then to get the direction, we need to use the formula for 2 theta s, which is minus sigma x minus sigma y divided by 2 tau xy. That would be minus 80 minus 50 divided by 2 times minus 25. So that comes out to be negative 2.6. Okay, so using inverse tangent, we get theta s, 2 theta s equals minus 69 degrees. So theta s is minus 34.5 degrees. Now this answer here comes with the sign, which means you need to interpret positive as counterclockwise, negative as clockwise. So that just means that we need to rotate the element clockwise by 34.5 degrees in order to get that particular plane stress element orientation corresponding to maximum shear stress. So it can be drawn as follows. So just as a reference, I'm going to draw the non-rotated configuration and then rotate this by 34.5 about its center. This is 34.5 degrees. Which is clearly clockwise. And then you can fill the dots about stresses by doing that. So for example, you see that's minus 15. So the stress would be like so. And then it says 69.6 for the shear stress. That would be like so, 69.6. Okay. And then you can, I forgot to do it for the maximum principal stress, but you can again reason the same way, just like I did it for this figure. So sometimes, you're asked to not only find the principal stress, but redraw the plane stress element in that configuration, in which case you're expected to show the stresses and the normal stresses and the shear stresses, just like I've shown in this diagram. Okay, so let's move on. I'm going to solve, well, I'm going to use the same plane stress element, but solve a different problem. So you get an idea of the various things which possibly can be asked with the Mohr circle. So here's the second example. Okay, so that's essentially identical to my first problem. There's no change in the stress element. Okay. However, the questions are different. So find or compute the stress when for a 30 degrees clockwise rotation of the plane stress element. And then the second question is draw the corresponding stress element. So when I say draw the stress element, you need to rotate it by 30 degrees clockwise, and you also need to show the stresses. Including direction. Okay, so again, I'm going to do this both ways. I'm going to do this using Mohr circle, and I'm also going to do it without using Mohr circle, using a different set of formulas. But in the same section, we had written these formulas, but never had used it before. So let's do it using Mohr circle first. So here's the first step here is to clearly draw the Mohr circle. Once you draw the Mohr circle, you can then do the stuff related to problem one. So instead of drawing the Mohr circle again from scratch, I'm just going to use the Mohr circle I'd drawn for this problem in the previous question. So I'm just going to copy paste that, and then I'll show you how to go about computing the part for problem one, part one of the problem. So let's grab I'm just going to grab the solution for this problem, just the Mohr circle. It's not here. Let's just put on a new page. We'll just erase this. We don't need this, nor do we need any of these things. Okay, so clearly the first step is to draw the Mohr circle. Okay, and then I should not have deleted this. Let me draw the line from A to B because I need it. Okay, so what I need to do for the first part is compute the stress for a 30 degrees clockwise rotation of the plane stress element. Okay, so you need to rotate either face A or B clockwise by 30 degrees. So you can choose point A or B, whichever you like, and then rotate it by 30 degrees clockwise. That's all I'm going to do. So remember that 30 degrees rotation on the plane stress element corresponds to 60 degrees rotation on the Mohr circles. That's the critical piece. So we need to rotate by 60 degrees clockwise. So if you do that, forget how much this angle is. I believe we computed that. Let's see. I'm just going to find what that angle is. This is the angle made by face A with the principal axis. So I just need to go back and find that. It's basically theta P, 2 theta P. 2 theta P is, yeah, here it is, 21 degrees. So I need that. This is 21 degrees. So I need to go 60 degrees. And remember that this is a right angle. So if I go 60 degrees from here, then I will end up with 60 plus 21 is 81. So there should be a 9-degree angle between the verticals. So what I mean by that is this will be something like this, where this angle is this angle, which is the rotation angle, is 60 degrees. And then you can see that 90 minus 60 minus 21 is 9 degrees. So it's 9 degrees off from the vertical. That's it. And then you can extend this on the other side just to complete the figure.
How did you find that 21 degrees?
Yes, good question. Let me go back. Okay, so what's 21 degrees? It's the angle made by the principal direction, the face A with the principal direction. Okay, that is, or the stress sigma b comma 0. So we had done this in the previous class where we had to find the angle made by the face A with the principal direction. So that was a calculation we did last time. So that is this angle, theta p. I actually had that was computed by using trigonometry. So by trig, you get 21 degrees for theta p, and I just used that. That's one way to do it. The other way to do it is what I just talked some time back, which is if you use the formula here, this formula, you can get 2 theta p as 21 degrees. That's pretty much what I used here. Right there. And I think this is, if you want to use trig, then this is what you need to do. You need to be careful about where this line lies, because as you see in the trig, you require the information. Okay, so I drew this blue dashed line because that's my new configuration. Let me just call that face A prime. Okay, so when A is rotated by 30 degrees, we get A prime, and then clearly B will also rotate because A and B are connected, they're right angles. Okay, so we got that. Now let's try to identify the stress here. What we're interested in is finding the stress, the x-axis, and the shear stress. So what we'll do is we'll use trig to do this. We know the radius of the circle. I think it was 69 point. So the radius is 69.6. If you can go back and check it. We also need the center, which is 15. So the center is at 15,0. And I think that's about it. Okay. So just so that to avoid clutter on that figure, I'm just going to draw just A prime, it's called the center as C, and this point. Okay. So this is the 9-degree line. This is the vertical line. This is our A prime. This is the radius, which I computed. And we know that this is 9 degrees. So this stress here on the stress, on the sigma axis is minus 15,0, which is basically the center of the circle. Okay, so I need to find this stress sigma, and this sigma is the stress, normal stress, and tau is the shear stress. So I just have to use trig here. So how do I do it? Well, I'm just going to use the fact that sigma is the distance from here all the way to this point. So it's going to be minus 15 minus r sine of 9 degrees. So if you can see, imagine this is r sine 9 degrees. So if you take this and subtract it out from this minus 15, then you will get a coordinate of A on the x-axis. And that's pretty much what I've done. Minus 15 minus 69.6 sine of 9 degrees. R comes from here. So that is minus 25.89. Now we need to find the y coordinate, which is the height here. So we can see that just by trig, this is r cosine of 9 degrees. And since it starts off with, it's about the distance is from the origin of the y-axis, so we just don't need to add any counterpart of 15 would be 0. So we can write the tau as minus or 0 minus, sorry, plus, because it's above the above the y-axis, r cosine 9 degrees. So that comes out to be 69.6 cosine 9 degrees, which is 68.78. Okay. So by the way, that is for A prime. If you wanted to find the coordinate of B prime, which is just diagonally opposite to this, you need to do the same construction for B prime. So sigma prime, tau prime, you can check that sigma. So compute, so try to do this yourself based on how I did it for A. Compute coordinates of B prime, and you should get coordinates of minus 4.1 for the x-axis and minus 68.78. Okay, so 68.78 kind of obvious because it's going to be the other side. The minus 4.1 actually comes because instead of having a negative, you'll have a positive. So it's actually kind of simple to do it. But I want you to go and draw this figure again and see if you can figure it out yourself. Okay, so we got the coordinates of B, and the coordinates of A, if you like, are, or A prime, sorry, are minus 25.89, comma 68.78. Just writing down sigma. Okay, so that completes part A, which was compute the stress for a 30 degrees. So the answer would be this is the answer, A prime, and then the answer for B prime. So we wrote the stresses for A prime and B prime. The next part is to draw the corresponding stress element and show the stresses. So what we need to do is now turn the element by 30 degrees clockwise and show these stresses which we just computed, but on the stress elements. Let's do that. This is just for reference. This is the original configuration that's rotated by 30 degrees in the clockwise direction. Okay, so if you like, this face now is A prime, and this face is B prime. Just write it here. Okay, sometimes it's easier if I just write these numbers here. Minus 25.89. A is minus 25.89 and 68.78. And then B is minus 4.1 minus 68.78. Okay, so the last part is to draw them on the stress element, which is rotated 30 degrees. So for face A, I need to put minus 25.89. Clearly, that's a compressive stress. So I will show it with an arrow pointing towards the plane stress element. Minus 25.89. And it's perfectly fine if we just show it on one side. And that's, you put the magnitude on one side. It's understood, it's the same on the other side. And then for B, it's negative 4.1, so again compressive, minus 4.1 BA, minus 4.1 MPa. Okay, now we come to the shear stress. So we need to use the convention we used for Mohr circle, which is, so for shear stress, the convention was clockwise is positive and CCW is negative. Okay, so first we look at the stress on face A prime. It's positive, which means the stress on the element at A prime would be clockwise. Okay, so clockwise is this way. So imagine what would happen if this stress was acting and it was free to rotate about the center point, it would turn clockwise. That's why it's clockwise stress. On face B, there's a negative sign, which means it's counterclockwise. Face B would be counterclockwise. Okay, and then we need to draw the stresses for the other two faces, and that basically follows from what is known as complementary shear, which says that if the stress on this corner is pointing, is tending to rotate this element in the clockwise direction as shown, then on the other face, adjacent face, it will be counterclockwise. If it was not, then it would actually start rotating, and that's not the case, right? It's a static element, doesn't rotate. And then on this face, same logic, it will be clockwise to beat the counterclockwise force induced to that. So we just write this down. The value of the force is 68.78. And we're done. So that is part B. Okay. Now, I told you that you don't really need to use Mohr circle to do this. This particular part, I use Mohr circle. You can actually solve this without using the Mohr circle. You have to, however, know the formulas, which I wrote down earlier. So the formulas we need in order to find the stress at an angle theta, in this case 30 degrees, is as follows. So another way. Without using Mohr's circle. Okay, so if you turn the pages, then you see that the formula I wrote down for transformation of stresses. So if a given stress for the plane stress element, then you can find the stress at an angle theta. And then that is sigma for the stress normal and tau for the stress along the plane. Finish this, sigma x, sigma y, tau xy. So there was a formula for sigma and tau, and that's pretty much what I'm going to write here. So the formula for sigma is as follows: sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine of 2 theta plus tau xy sine 2 theta. And then there's another formula for shear stress, that is sigma, it's negative sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy cosine of 2 theta. Okay, and we need to sub in the values for sigma x, sigma y. So sigma x follows the same convention. Sigma x positive when it's tension. So in this case, it's compression, 80 MPa. Sigma y is here it's in tension, it's 50 MPa. And as I told you, the convention for tau is that when we take the shear stress, this is in the derivation, the shear stress was taken to be counterclockwise on face A. When it's counterclockwise on face A, the convention says that that should be the positive direction, because we use that convention to do this derivation for sigma and tau. And so if you look at this figure for in the problem, we saw that the shear stress is not in that direction which we derived it. So it's the opposite direction. So it's minus 25 MPa for the shear stress. So tau xy is negative 25 MPa. Okay. The convention here is counterclockwise or CCW on face is positive. Okay, so then, well, we have one more piece of information. What is theta? So theta is the angle, and you can see that the convention is that the angle counterclockwise is positive. In this case, we are trying to rotate the element clockwise, and so since it's clockwise, we need to put a negative sign because rotation is clockwise. Okay, so what remains to be done is to sub in these values for sigmas and taus and theta in those formulas. If you do that, you get sigma equals minus 25.85, and then tau equals minus 68.79. Okay. Now notice that we have to find the stresses on both faces. We just found the stress on one face. If you look at the previous answer, we got two answers, right? We got one answer for A and we got one answer for B. Here, if you look at the answer we got, it's actually face A. This is the stress on face A in the rotated configuration, which we call A prime. Okay, so how do we get the stress on the other face, which is face B? So what is the stress on B when it's rotated? We call it B prime. So in order to get that, what we can do is we can look again at the plane stress element. So this is the plane stress element. And then if A is here, B is there. If you want to find that stress, you only need to take and sub in theta as theta plus 90, and you should get it. Or if you want to, if that's not satisfactory, then what you can do is you can rotate this element by 30 degrees clockwise. And then ask yourself, what is the angle made by face B in this rotated configuration? So this is A prime, this is B prime now. This angle is 60 degrees, right? Because this is 90 degrees. It's right angle. So 90 plus 60 plus 30 should be 180, and that's what the sweep is. So all I need to do is I need to put theta equals 60 degrees. And I should call this formula something. Let's call this formula 1 and this one formula 2. So I need to put essentially theta equals 60 degrees, and then I should get the answers for face B. And say put or substitute theta equals 60 degrees in 1 and 2. And then if you do that, you will get sigma equals minus 4.1. Oh, I did a sign error. I think I did an error here. This should be positive. You can check me on this. Should be negative. And then here you should get a negative one. Minus 68.79 MPa. is face P or P prime. Okay, and then this is just solving for the first part, that is the stresses on face A and face P. The next step is to draw the stress element, the rotated configuration, and show the stresses. That you can do. You know what? I think I'm my bad. This is actually negative. Sorry about this. And this is positive. If I didn't realize, so you should actually get into, so this is negative, this is negative, but you will see that it doesn't actually match with the answer I had for the Mohr circle. If you look at this, it's positive for A and negative for B, and you got exactly opposite for this. And this should be the case because the convention is that whatever you got for the Mohr circle is going to be reversed for the plane stress element, right? So this is actually the right answer. And you should check this. In my notes, I'd actually done this calculation, and I just skipped me that it should be the same. It shouldn't be the same. You can put these values and check the value. It should be negative, not positive. Okay, but the answer which you get for the stress element in terms of stresses, which I drew over here, will be the same. So, for example, in this case, we got stress was negative 68.79, right? So negative 68.79 by our convention, which I drew here, right? Our convention is this way is positive. So what this is saying is, I can quickly draw this here. In the rotated configuration, this is negative, right? And negative is clockwise. So it should be like this. This is going to give me this because of this convention, not the Mohr circle convention. And then if you check this direction with what I've shown for this for the previous page, for the previous is that right here. So it is the same direction. Okay, just that the signs were different. This is a point of confusion, but just be mindful that if you use this method, you want to stick to the convention of the figure which I drew here.